From the beautiful South Studios of Way Happy, this is Mr. Meyer, and we are going to chapter 26 in the book you actually have. It is called Bivariate Statistics, and I highly recommend you do read the little bit before the problems. But I'm going to kind of summarize it here. And what is it? The first thing we got to talk about is a correlation, right? And a correlation is just a relationship between any two things, and you usually would call them data points, right? Maybe we will take my age and my IQ, and as I plotted those over time, I slowly see a relationship, right? And so maybe that would be called a correlation, and you could pick this with lots of data. Now, sometimes there's positive correlations, like my age and IQ. It looks like as I got older, my IQ went up. So that would be a positive correlation. You could also have data definitely that goes in a negative way, right? In a negative correlation. Something that looks like it has negative slope. Now, speaking of slope, some things could be linear and some could be non-linear. What does that mean? That just means it looks like, hey, look, that data that I just drew there on the right, that looks like a nice straight line. But maybe you might have data that kind of looks like a straight line and then it starts to take off really fast, right? And space out. And maybe it looks to you more curved, more parametric. Right? So that could happen. So you could have linear. If you look at the data, it could look linear. It could look non-linear. It could be strong or weak correlation. What that means is when you do like a line of best fit, right? Where you try to make a model equation that fits this data, a strong correlation, everything would be really closely tight to that line. You're like, yeah, man, all those data points are really close, as opposed to maybe a weaker one that has data points like this, right? And you're like, oh, I'm not 100% sure. Like the line could go through here, but it's not the best line. In fact, maybe the line should have been more like this, or maybe somebody's like, no, it's like this, right? And so you could have kind of scattery points where a line might not fit that well, and that would be a strong correlation, or I'm sorry, a weak correlation. Strong, very tight, close knit. Like I would call this a strong correlation right here. Right, that definitely looks like a nice strong correlation. An outlier, you could definitely have when you graph, you might have a bunch of points that are like beep, 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 and they look like they're going on this nice strong linear correlation, and then there's one up here, right? And you're just like, what the, right? That just happens, right? And it could have been, again, an error, and if it is, and you're like, oh, we used the wrong measuring tool, you throw that one out, right? However, if it's not an error, you should keep it. Right? It is part of data, and there's some data that's weird. And then causation. Causation is probably the one that I wanted to warn you about the most, because people seem to think that they see data that the two are related, and they don't have to be, right? Like my age and IQ probably related because I learned more as I got older. However, take something else like my age and the graduation rate at Granada. And let's just say, as I got older, more people started to graduate, right? And you're like, wow, look at that. That's a nice, strong correlation. It's positive. Everything's good. And then some people might throw in some causation that the older I get, the smarter Granada gets. And that's probably not the case, right? That just might be a neat coincidence, and I could feel good. But some people would see it on a graph and they would believe that to be true. So I want you to realize that just because the two things have a correlation, it doesn't mean there is any causation. And that's it. Have a great day. Stay happy, and we'll see you next time.